Hello everyone, welcome to MK Academic Solutions. So in this video, I am going to explain you about the effect of temperature on equilibrium constant and Arrhenius equation. So these are the topics actually I said that I will cover in the last video, but due to the time lapse I did not cover it. Now I am going to cover these topics. Okay, so now let us go to our topics. The first one is effect of temperature. Effect of temperature and Van 't Hoff equation. So what is the effect of temperature? Okay, so temperature changes the rate constant. Temperature changes the rate constant and also changes the equilibrium constant and also changes the equilibrium constant okay. So now let us see how it is going to change the rate constant and also equilibrium constant. Okay, now let us take the thermodynamic relation. Okay, thermodynamic relation. So what is the thermodynamic relation? Thermodynamic relation, we'll see here. Thermodynamic relation, that is delta G is equal to delta G naught plus RT ln Q. RT ln Q and consider this as the equation number 1. Next, delta G naught is equal to delta H naught minus T delta S naught. This you consider as the equation number 2. Okay. So now here what is delta G naught, delta H naught and delta S naught? Delta G is the change in Gibbs free energy. So here delta G, here what is delta G? Change in Gibbs free energy. Next to delta G naught, standard Gibbs free energy change. Standard Gibbs free energy change. Next, delta H naught is standard enthalpy change. Delta H naught standard enthalpy change. Next, delta S naught is standard entropy change. Okay. Delta S naught is standard entropy change. Standard entropy change. What is this standard entropy, standard enthalpy? I explained in the thermodynamics chapter. Okay, you can watch there. Okay, so these are the things. Okay, now let us take the condition. So here we know Q is what? Q is the reaction quotient. Okay, so here what is Q? Q is equal to reaction quotient. Okay. Standard entropy change. Standard entropy change. Okay, and Q is equal to reaction quotient. Reaction quotient. Okay, right. So this we know. These are the relations. Now let us see. Let us take at equilibrium. At equilibrium, what are the conditions here you will get? At equilibrium, Q will become K, means QC will become KC, means reaction quotient will become equilibrium constant, and delta G is equal to 0. This thing will happen. Okay, now let us see. We know delta G is equal to delta G naught plus RT ln Q, right? So now at equilibrium, at equilibrium, so what happens at equilibrium? We know at equilibrium QC is equal to KC, delta G is equal to 0. Therefore 0 is equal to delta G naught plus RT ln K, RT ln K. Therefore delta G naught is equal to minus RT ln K, right? Now consider it as the equation number 3, and we know one more, that is delta G naught. One more relation also here we know, that is delta G naught is equal to delta H naught minus T delta S naught, delta H naught minus T delta S naught. Okay, these are the things we know, right? So now this equation I considered, actually it is the second equation in the previous one. See here. So this is the equation. Okay. So now when you compare this here, LHS equal to means RHS also will become equal. So now minus RT ln K is equal to delta H naught minus T delta S naught. Okay. So or else simply what you can write is minus and you send that side, RT ln K is equal to minus delta H naught plus T delta S naught. Okay, right. Now you said RT, that side what will happen? Ln K is equal to minus delta H naught by T, or RT plus T delta S naught by RT. Okay. So now here T will get cancelled out in this equation. So therefore ln K it is nothing but Kc only, ln K or ln Kc. Okay, Kc only, right? ln Kc is equal to minus delta H naught by R into 1 by T plus delta S naught by R. So this is the want half equation. This is what? Want half equation. Want half equation here. So now here this is consider, let us consider at temperature T1, at different temperatures we are going to take. At temperature T1, ln Kc1 is equal to minus delta H naught by R into 1 by T plus delta S naught by R. Next, at temperature T2, at temperature T2, ln Kc2 is equal to minus delta H naught by R. So this is T1 into 1 by T2 plus delta S naught by R. Okay. So now let us consider this as the equation number 4 and this is the equation number 5. So now let us do the 5 minus 4. Let us do the 5 minus 4 and condition you apply. T2 is greater than T1. T2 is greater than T1. Okay. So therefore, what you get here now? ln Kc2 minus ln Kc1, or else we will do in the new page. So this we know, right? You remember these equations. ln Kc1 is equal to minus delta H naught by R into 1 by T1 plus delta S naught by R. So now you remember that equations. Now let's see here. 5 minus 4 means ln Kc2 minus ln Kc1 is equal to minus delta H naught by R into 1 by T2 plus delta S naught by R. Delta S naught by R. This is one. Another one minus delta H naught by R into 1 by T1 plus delta S naught by R. Okay. So these are the equations. Okay. Now, so ln A minus ln B, it will become ln A by B, ln Kc2 by Kc1 is equal to ln Kc2 by Kc1 is equal to minus delta H naught by R into 1 by T2 plus delta S naught by R minus into minus plus delta H naught by R, delta H naught by R into 1 by T1. So minus into plus minus delta S naught by R. Okay. So here now this delta S naught by R, delta S naught by R will get cancel out. Okay. So now what is going to be remain here? ln Kc2 by Kc1 is equal to minus delta H naught by R into 1 by T2 plus delta H naught by R into 1 by T1. Okay. So now what we are going to consider here, you take the common. So what we are going to take the common, delta H naught by R, you take the common. Okay. So ln Kc2 by Kc1 is equal to delta H naught by R, you are going to take common. Or minus, or simply take the delta H naught by R common. Delta H naught by R if you take common, minus 1 by T2 plus 1 by T1, or else ln Kc2 by Kc1, that is equal to delta H naught by R 1 by T1 minus 1 by T2. Okay, so now this we can write as, how we can write it as ln Kc2 by Kc1 is equal to delta H naught by R T2 minus T1 by T1 into T2. So this is known as what, children? Want half equation. Okay, this is known as what? Want half equation. Want half equation. So now here, by using this relation, we can find the ratio of Kc2 and Kc1 at different temperatures. Once if you know the delta H naught and R values and T1, T2 values. Okay, so this is about what? Effect of temperature. Okay, so now okay, right. Next, let us discuss some important facts about the reversible reaction. Let us discuss some important facts about the reversible reaction. See here. So what is the thermodynamic relation? Here we are having ln Kc is equal to minus delta H naught by R into 1 by T1 plus delta S naught by R. Okay, so here if reaction is exothermic and endothermic, exothermic reactions and endothermic reactions we are going to consider. For exothermic reactions, children, delta H is equal to negative. Here endothermic reactions, delta H is equal to positive. See here, delta H is negative. Negative into negative will get what? Positive. So therefore Kc is greater than 1. Kc is greater than 1 means more amount of products are present. And here Kc, here positive means positive into negative will get what? Negative means here Kc will become less than 1. And some more conditions also we can apply. What are the conditions? Delta S naught. What is the delta S naught here? Standard entropy change. Standard entropy change means what? What is the meaning of standard entropy change? Means disorderness, system disorderness. If delta S naught is, if delta S naught is more positive, if delta S naught is more positive, if delta is not, what I am telling here, more positive, more and more positive, and it reduces this value also, then that time here Kc again you will get the greater than 1. If delta S naught is more negative, delta S naught is more negative, so means this positive value also will become again negative, means here Kc is less than 1 will get. Delta S naught is more negative means this actually delta H naught is negative, no? Negative into negative, positive. This we are getting positive value when we are going to consider delta S naught somewhat little bit only, and it is positive only we are going to consider. So totally if you get this positive value, case may be greater than 1. But even in exothermic reactions also, if delta S naught is more negative, delta S naught is what? More negative. Okay, even if you increase the temperature also, case is going to be decrease. Okay, next, if here in this case, if delta S naught, if delta S naught is more positive, if delta S naught is more positive, so here actually delta H is positive, no, positive into negative will become negative. But here one more term also is there, delta S naught. If delta S naught is too much positive, so that this negative also will become positive, then that time Kc is greater than 1, equilibrium constant greater than 1 will get. And one more thing here, if delta S naught is negative, if delta S naught is negative, if delta S naught is negative means here already here we are getting the negative value, again it is also negative means total Kc will be less than 1. Okay, and one more condition, if delta G naught, okay, so these are the important conditions about the van 't Hoff equation and thermodynamic relations. Okay, next let us discuss. So this first topic is finished, effect of temperature on van 't Hoff equation. Okay, so generally temperature increases, endothermic reactions increases, exothermic reactions decreases, and overall relation we can get from this relation, van 't Hoff equation relation. Okay, so the overall relation we can get from this van 't Hoff equation, what happens to an exothermic reaction and endothermic reactions. Okay, right. Next, let us see Arrhenius equation. Arrhenius equation, we will see what is the Arrhenius equation. Arrhenius equation. Arrhenius equation. Okay, what is Arrhenius equation, children? Arrhenius equation, K is equal to A into e to the power of minus Ea by RT, or ln K is equal to ln A minus Ea by RT. Okay, this is the Arrhenius equation. Now here we are using Arrhenius equation to find out the equilibrium constant. Okay, we use the different activation energies, right? Okay, therefore, see, let us consider this is the A is gives rise to B, a reversible reaction. It is the forward reaction, and it is the backward reaction. Okay, so now let us consider here, consider Kf is the rate constant of forward reaction, rate constant of forward reaction, and Kb is the rate constant of backward rate constant of backward, and next AF is the Arrhenius factor for forward, Arrhenius factor, Arrhenius factor for forward reaction. AB is the same Arrhenius factor for backward reaction. And next to EAF is activation energy of forward reaction. EAF is what? Activation energy of forward, and EAB is activation energy of backward. Activation energy of backward. Okay, so these are the conditions we use. Next, so Arrhenius equation for forward. Okay, so these are the conditions we know, right? So now let us see Arrhenius equation for the forward and Arrhenius equation for the backward. So now I am going to use this. ln Kf is equal to ln AF minus EAF by RT. Same temperature we are going to take. Next, consider this as the equation number 1. Next, ln Kb is equal to ln AB minus EAB by RT. This is the equation number 2. So now what we will do, equation number 1 minus equation number 2 we will do. Okay, so now let us do 1 minus 2. So when you do the 1 minus 2, what you will get? ln K forward minus ln K backward, that is equal to ln A forward minus EAF by RT minus ln A backward minus EAB by RT. Okay, so now here ln Kf by ln Kb, ln Kf by Kb, that is equal to ln AF minus EAF by RT minus into plus minus ln AB minus into minus plus EAB by RT. Okay, so this is the relation here you will get. Next, ln Kf by Kb is equal to, so here ln AF minus ln AB, ln AF by AB, so here plus EAB by RT minus EAF by RT. Okay. Now in this you take the RT common, ln Kf by Kb is equal to ln AF by AB plus 1 by RT EAB minus EAF. Okay, so this is known as what? Arrhenius equation. It is the what it is? Arrhenius equation. So now here, what is ln kf by kb means? Kf by kb means ln kc you will get. Ln kc you will get, and here ln af by ab plus 1 by rt EAF by EF minus EAB. So this in place of ln, if you want to write 2 point natural logarithm, how we can write? So simply natural log Kc is equal to log AF by AB plus 1 by 2.303 or EAF minus EAB. Okay, EF minus EAB, or simply write here only. Okay. Right. Okay. So now let's see here. Instead of ln kc log, I am going to take the log kc is equal to log AF by AB plus 1 by 2.303 RT. So EAF minus EAB. EF minus EAB. Okay. So this is about what? Arrhenius equation. Arrhenius equation at for so by using the Arrhenius relation also we can calculate what? Kc. Okay. So here different activation energies at for forward reaction and backward reaction, and temperature is same, R is also same here. Okay, right. This is about what? Arrhenius equation. Okay. So based on this we can do some numericals also, but this numericals they may ask in the advanced level. Okay, you just sometime directly they may ask which is the correct relation for the Arrhenius equation. Okay, this is about the correct relation of Arrhenius equation. Okay, so in this video what I have explained you, this video I have explained you about chemical equilibrium, so lecture number 5, effect of temperature and want half equation, and here also we discussed about thermodynamic relations, thermodynamic relation and the want half derivation. And next I explained you what is the derivation for the want half equation, and this is the final derivation, and conditions also I explained you all these things. So this is the relation between the Kc1 and Kc2, means what happens if you change the temperature for the Kc. Next conditions, exothermic reactions, endothermic reactions. In a competitive exams directly they will ask this one. Okay, directly they will ask exothermic reaction, delta H is negative into negative, positive. So this you just consider it is somewhat small positive only, small change only, means Kc is greater than 1. Delta S0 is also more positive, it is also positive, still we will get the Kc somewhat greater than 1. But in case of delta S0 is more negative, it is more negative, and it is cancelling all this positive value also. What will happen? Kc is going to become less than 1. Okay. And next for endothermic reaction, delta H is positive, just consider this term is negligible is there, means Kc is less than 1. Why? Because positive into negative it will become negative, means Kc is less than 1. Next, if delta S naught is more positive, if delta S naught is more positive, so and this negative value also will become positive. Why? Because more, it is more when you compare to this negative value. Positive value is somewhat higher when you compare to this negative value, means this total will become what? Positive. So therefore Kc will become greater than 1. If delta S naught is more negative, this is also negative and this is also negative, means Kc will become negative. Okay, so this is about the effect of temperature and thermodynamic relation. See here, generally temperature is in the denominator term. Okay, temperature increases, what will happen? This total term is will become positive. This total term will become what? Positive. Okay, and for this graphs also I have explained in the previous videos. Okay, and they may ask the graphs also. And next, then after I explained you Arrhenius equation. This is the Arrhenius equation. So by using Arrhenius equation also we can calculate the equilibrium constant. So here what we are doing, we are writing the Arrhenius equation for forward reaction and backward reaction. So now next we are going to subtract the Arrhenius equation forward reaction 2 from the we are going to subtract the Arrhenius constant for the backward reaction from Arrhenius equation for the forward reaction. Okay, and next you see, this is the derivation, total derivation. Okay, so final equation you remember, derivation is not necessary, final equation you remember for the competitive exams. Okay, so with this I am going to end this video. Okay, thank you for watching. Thank you for watching. Okay, right.